Hi, my name is Miloš and welcome to Element 14 Presents. Today we will continue work on our PlatypusBot from last time. This time we're going to learn about encoders, we're going to learn about PID controllers, and we're going to make some highly requested additions. Let's get to it. If you haven't watched the last video, this is the PlatypusBot. So this is a small mobile robot platform that I made from discarded parts from an old Roomba. So I literally utilized the motors because they have encoders and nice gearboxes, and it was controlled by via joystick over Wi-Fi using an Arduino Uno R4 Wi-Fi. This time, however, let's upgrade it to actually be more of a standard robotics platform, so we can actually do some more capable algorithms, and that's something I teased the last time in the video by adding a Raspberry Pi 4 and adding this slider on top that we will use at a later point. This time we're gonna focus on the Raspberry Pi, adding robot operating system to it and controlling the Arduino using that robot operating system. But before we get to that, let's figure out how these motors work by disassembling one and seeing what's inside, how we can read encoder signals, and how we can utilize that to actually precisely control our robot. Here's one of the drive motors from the PlatypusBot that you've seen in the last video. This time I'm going to take it apart in more detail and show you how everything works. So I'll speed up the boring processes. Okay, that's the cover off, and here you can see the encoder cage, and I'll get into more detail on how this works during this clip. Okay, and here's everything disassembled. Here we can see the full gearbox and how it looks. So if I take a pair of tweezers and lift this gear up here, you can see that the motor spins this first gear here, which then spins this intermediary gear, and then at the end we have the big gear that is attached to the wheel. So let's get back this gear on its axis. I'll count the teeth and explain the gearing ratio in the next clip. So it popped back in. Here is the small motor. It's just a brushed DC motor that's spinning that gearbox. But now the thing we're most interested about at the moment is this. So if you take a close look here, you can see a bunch of teeth like a cage. So this is the encoder wheel, and here we have the photo detector and the photodiode. So essentially, since they're sitting next to each other like so, you can imagine the teeth coming between them, and they're breaking the signal, and that's what we use to actually know the position and the speed of the motor. And the wheel itself. I'll show you that calculation now. It's rather simple, and then we'll experiment with how we can actually make controllers that can utilize this encoder. But before that, let's just quickly assemble the motor back. And we have it completely assembled. Let's go and take a look how it actually works when it comes to the encoder reading and the whole gearing. Let's draw out what we've just seen in the actuator. First we have the gears, and here is the gear arrangement that we've seen. First we have the motor gear, then we have the two gears in the middle, and in the end we have the output gear. So what we need to do now is count the teeth, and that's what I did off camera. So the motor gear has 11 teeth, the gear 1 has 11 and 36, gear 2 11 and 42, and the output gear has 54. Why do we need the teeth count? Is so we can calculate the gear ratio. So we know how many times the motor needs to spin in order for the output wheel to spin once. Now, what we also have on the actuator, as you've seen, is the encoder. This is the encoder wheel that's on the motor. It actually has 20 teeth, not the 12 that you can see in the drawing, but you get the idea. How it works, we have an IR LED and an optical sensor, and as the encoder wheel is spinning, it's breaking the laser beam, or the light beam, and that's what the optical sensor is detecting. If we draw the graph of that, we can see how that would look for a constant speed case, where you would literally see just a square wave signal. Now, because we're just gonna use some resistors to read it, it won't be an actual square wave. In ideal conditions, the on time and off time would be equal, but because we're gonna observe something different, as you will see in the next clip, we're gonna use the whole signal period instead of the on time and off time. If we could, however, use the rising and falling edge, which would be the case where the on and off time are equal, then we can read the encoder in quadrature, which means we could actually increase the resolution, but we don't need that high of a resolution here. So the only thing that we will look at here is that for every spin of the motor we have 20 pulses. Now, before we calculate everything, we need the outside circumference of the wheel, and I measured that to be to around 205 millimeters. Now, if we calculate how much the wheel needs to spin for the robot to actually move 1 millimeter, that's 360 degrees divided by the 205 millimeters, and we get to the angle of 1.756 degrees. And on the other hand, if we see how much one pulse is actually in degrees on the output wheel, we have the 360 degrees again, we have the 20 pulses and the gear ratio, we come around to the number of 0.2934 degrees. Now, if you take a closer look at these numbers, if we divide one by the other, we get a number that's almost a round number, and we're gonna round it out to 6. What this means is that we're actually gonna have 6 pulses for 1 millimeter of movement, which makes our life really easy for all of the control algorithms, as you will see later in the video, and this is what we will be using in the rest of the code. Before we get into the motor testing, let's check out the final electronics for this stage of the PlatypusBot. So like last time, everything is powered by a 12-volt battery, but this time I added a buck converter to step that down to 5 volts so we can power the Pi, and I just made sure to use a buck converter that can handle a couple of amps so that the Pi can work properly. Besides that, we have the Arduino like we did last time, and this is how we connect the motors to the driver and to the Arduino. So the only new thing is this. As you've seen in the drawing also, we essentially just have to pull up resistor for the detector and just a current limiting resistor for the LED itself, and that's how we are reading the signal. Let's go and test the motor before we actually put it all together. Everything is connected as you've seen in the drawing, and now we can see what the scope can read. So if we turn on the power supply now, you can see a square waveform and you can see the wheel spinning. You can also see the frequency down there as the readout, and this is at 4.7 volts, so if we increase the voltage to, for example, 8 volts, you can see how the frequency increases. If we go further, it will just continue increasing further and further. This is at around 12 volts, and this is what we expect. The faster the motor is spinning, the shorter are the pulses that are generated by the encoder. I've also connected the Arduino to read the signal with a digital pin, and if we go to the serial monitor, we can see a similar waveform, but this is not that accurate like this because this is just reading it. Now I will show you how to do this properly using an interrupt routine with the Arduino Uno. Now that you've seen how the signals look from the encoders for each of the motors, let's utilize that to actually control the motors by having them at constant speed or going a set distance with them. How we're going to do that is by using PID controllers, and that's the next thing that I'm going to show you how it works, and then we're going to implement it and test it. Let's take a look at how a PID controller works. PID stands for proportional integral derivative, and I'll get into the specifics of each one of those later. So let's first imagine the PID controller as a black box with some inputs and outputs, 2 inputs, so reference and a sensor, and just some kind of an output signal. In our case, we will give it a speed reference, the speed measured by our encoders, and a PWM duty cycle that will go to a motor drive. But what's actually happening inside this black box? So here is the diagram of that. We have the three components Pi and D. We are summing them and getting them to the robot or to our actuator. We are reading the encoder signal, then in a piece of code we are converting that signal to the speed measurement, and then we're subtracting that speed from our reference, getting our error signal. The idea and the purpose of the PID controller is to actually minimize that error, ideally to have it at 0. Now let's take a look at each component of the PID controller. So as I've said in the beginning, we have the proportional part, the integral part, and the derivative part. The proportional part is the simplest one. This part adjusts the output based on the gain and how far you are from the reference. So you can imagine if you want to go at 100 kilometers per hour and you're going 50, for example, you're gonna press the throttle more than if you were at 8. The integral part of the controller works by using the integral gain and the accumulator is just the sum of all of the errors so far. It really helps with correcting the steady state error. So for example, if with the P controller you get to around 95, the integral part will get you just right around to the 100, as you will see later on in the video. And in the end we have the derivative part, which works with how fast the error is changing, and that helps with overshoots. The actual output of the PID controller is the sum of these three components and is represented by this formula here. Now, this is just some random math now on your screen, so I'll try and draw you a graph to get this a bit closer to you so you understand how it works. So here is our graph. The yellow line is a reference, so we just want at some point our speed to jump from 0 millimeters per second to, for example, 10 millimeters per second. Doesn't really matter the number. Ideally, our controller would follow this reference completely like this with 290-degree turns, but that's impossible, as we will see. So let me first draw how a P controller would look like. It would be something like this. And as you can see, it increases the speed when the reference jumps, but it never actually reaches that reference. There's always that steady state error. Now, if we added the integral part of the controller, we would see something like this. The signal would rise a bit faster and we would have no steady state error, but you can see that we have a bit of an overshoot here. If we added the derivative part too, and this is of course if everything is properly tuned, we can then lower that overshoot and get a controller that follows the reference much better. And when I say tuning the controller, that just means adjusting the proportional, integral, and derivative gain and see how your output looks like. Now, because of non-infinite acceleration, you can never get an ideal controller that follows the reference, especially for step references. But they work really good, especially for real systems, and I'm gonna show you an example of how this works with our actuators. Time to implement those PID controllers now in code. So we're now in Arduino IDE. First we have the libraries and the pins, followed by all of the parameters and variables. Here you can see where we can tune our controller by adjusting the gains themselves. So let's first go to the setup function to see how this code works. Essentially, it works on interrupts. Two of these interrupts are for the encoders. These are hardware interrupts, and that's why they are connected to pins 2 and 3. Because those are the only pins that actually support hardware interrupts. Besides that, we have timer interrupts. One is for the PID, this is timer 1, and the other one is just for general control, this is timer 2. So let's first go to and check out the PID and how it works. First, based on the reference, we need to figure out the direction of our motor spinning, so that's just if we want it plus or minus essentially. So we just do that in one line. And here is the whole ordeal with the PID as I've shown you in the drawing. We update the last error with the error. This is just some filtering because of the noisy encoders. We calculate the error, add that error to the accumulator, and we calculate the output of the PID controller based on the formula that I've just shown you. That's essentially it. I didn't even do any things like anti-wind-up stuff like that. It worked pretty okay like this, but we can go into more details and more advanced controllers for the next setup, and we're gonna have more capable drivers. And all I did do here is just make sure that the PWM value is between 0 and 100. I do exactly the same thing for the motor too, and in the end we just send that control to the motor. That's it. As for the other timer, this essentially controls when we receive a command, whether we wanted a speed controller, position controller, stuff like that. It's just some simple logic, and you can find this whole code on Element 14 community and on GitHub down below. One thing that I want to point out here is how the commands work. So these are rather slow commands and not something that you can send at high rates, but that's what I want for this stage of the robot, just to be able to give it some simple commands. So it's powered by G-code and literally sent like this through the serial monitor. You can see the 6 commands I implemented. I always implement C0 as stop everything, because at that point the robot is gonna fall off the edge or it hits something, so I just want to kill it. Besides that, we have the enable disable the motor driver just by driving 2 pins high or low. We have the constant speed timed move, relative position move at set speed, tank turn, which is when the robot turns in one spot, and we can manually drive the wheels with this command. How this works is we check whether how that command starts. If it starts with C2, we know that we need to then find the S and T in that message and then parse these parameters and then later get them through the system. So that's the whole code. It's rather simple right now. Let's go and test out the PIDs and this code on the robot itself. We're finally back working with the robot. So you can see this black line here on the wheel that I marked. And now when I turn it, you can see on the serial monitor that we're getting outputs of speed that it's actually being able to get. So I'm just using the 6 pulses as 1 millimeter, since it's a pretty good approximation. So let's try out the commands that you can see above here. So first of all, we need to enable the driver, so that would be it. And for example, let's move the wheel by 205 millimeters, so that should be one full circle at speed 200 millimeters per second. So it won't be too accurate, but let's see how it goes. Let's do another turn. As you can see, there's a bit of an offset, but for what we need and how we want to control it, especially with these encoders, that's really good. We can also do something like constant speed. So let's say at 150, and let's do that for 3 seconds or 3000 milliseconds. So look at the serial monitor output when I press enter, which is now. You can see that the controllers for both wheels are doing their job rather good and keeping the speed at around 150 millimeters per second, which is what we wanted. We'll see the rest of the commands when we start testing the robot, but now we know that both the speed and the position controllers are working, so we can continue and get this connected to ROS. Last thing we need to talk about is ROS. What ROS stands for is Robot Operating System. We're going to be using ROS2 or ROS2 Humble to be more specific, and it's the middleware that we will be running on the Raspberry Pi 4. So what's the deal with ROS? What is ROS? I'm going to give you more details in the next clip, but the things that we're going to focus on now are 3 things. Those are topics, those are nodes, and those are services. So how ROS actually works is you have your chunks of code and they're called nodes. And those nodes are actually codes in themselves that run in a, let's just say, in a loop, and they communicate between each other using topics, which are messages that are constantly being printed out, and services which are event-based. Why is that so important? Because it lets us modify or add another sensor or something like that without changing the main code and breaking something. I think you'll get a better idea of how it works when I do the next drawing. But if you want to install ROS2 the easiest way on your Raspberry Pi 4, I have this GitHub page here that I found with the real-time kernel. You can find it linked below in Element 14 community, where you can get your fully set up image for the Raspberry Pi 4, or Raspberry Pi 5 actually. So let's go and dive deep into ROS2 now. Let's talk about ROS. ROS stands for Robot Operating System, and what I'm about to say is true both for ROS1 and ROS2. There are some differences, but I won't get into them here. So, first of all, ROS is a middleware framework that's mostly used for robotics, as the name suggests. It's completely modular, and that's really important, as you will see through this drawing, and we're going to focus on three main things here. These are nodes, topics, and services. What are nodes, topics, and services? Imagine nodes as independent parts of code running in a loop. That's literally it, just chunks of code. You can imagine topics as message channels to which you can either subscribe to read messages from or publish data or messages to that topic so other nodes can subscribe to those topics. And we have services which are like event-based interfaces pretty much, where you just send some parameters to a node and you can get some data back. To explain this a bit further, I'm going to draw you a simple 4-node system that you can pretty much expect to see on a simple robot. So imagine nodes as these circles here, and let's start with node 1. Let's say node 1 reads IMU data and publishes that to a topic. That's all it does. So it reads data from an MPU 6050, for example, using I2C, and publishes that to the IMU_data topic. That's all it does. Node 3 can be the PID controller. It subscribes to that topic from the IMU node, and it also subscribes to some kind of a reference topic. It calculates the PID output as I've already shown you and publishes that to the PID output topic. Node 2 can be a controller node where we have a service as an interface that sends a different reference sequence based on the service call. So as a user you would, for example, send the command for the robot go straight 200 millimeters or something like that, and the node would recognize what kind of reference it needs to send to the PID controller so that it can send that further on. In the end, we have the node 4, which is the interface node that actually just communicates with the hardware itself, so that if this is running on a Raspberry Pi, you have a node that just communicates with the Arduino. But why is this so good and important? Imagine, for example, that in this case we don't want to use a PID controller, the performance is just not what we want, but some other new one. Instead of changing the whole code and risking breaking something in the process that works, we can just change the PID controller. We can do that by simply adding a new node. For example, we can add a new control node and connect it to the same topics as the PID node, and we just wouldn't run the PID node, and the system wouldn't care, wouldn't even notice, and we would have a completely different setup without risking breaking the sensor readings, the user interface, or the interface with the microcontroller. We would know that all of those work. The same thing would be if we, for example, find a new IMU and it uses a different protocol. We would just put a new IMU node, IMU2 node or whatever it's called, and it would read the sensor data and publish it to the same topics, and the rest of the system wouldn't care. This is why it's so great to work with ROS, because it's really easy to change stuff, whether it's add new sensors, change sensors completely, or delete part of the code without affecting everything in the system, without breaking essentially everything. Let's see how we will use ROS for our robot. Now that you've gotten the basics of how ROS works, it's time to program our first node. So first I'm going to show you how you can make a simple publisher node where it just publishes a counter on a new topic that it creates. And then I'm going to show you the node that I made for communicating between the Raspberry Pi and the Arduino. It's going to be really simple for this stage of the robot. All I want to do is create a service where if I input a string command, that command will be sent to the Arduino using the protocol that I've already shown you, so we can actually control the robot. That's enough for giving it some simple commands like movements to navigate around, but at some later videos we can integrate sensors, we can integrate LiDAR and some more complex algorithms. So let me show you how you can program in ROS using Visual Studio Code and how you can make your first node. Before we get to the final code in ROS 2 that I'm gonna run on for the PlatypusBot at this stage, let's see how we actually work with ROS. So now I'm in Visual Studio Code and the Raspberry Pi is powered and it's connected to my internet. This is the IP address, and this will actually give you remote access to the Pi. Let me just enter the password and connect it. Okay, now that we're here, we can open the folder and we want this folder. Okay, let's wait for it to open. And here we are. So we're now actually connected to the Pi, and this is what we can see. Here you can see some of the packages I have. The most important thing, so this is not a new installation for me. You need to create this directory ROS2 WS, and you need the source directory. After that, we can, for example, we can check the packages, we can check the version of ROS, stuff like that. I also have a command to check the temperature of the Pi, so now it's at 63 degrees and so on. So first of all, before we get to the code, I'm just gonna show you a simple way of just creating a simple publisher node so you can see what I was talking about in the drawing. First of all, we need to do this. This command creates a package, and it's just a simple node that will publish messages. So we run that command, and here on the left you can see that will be, sorry, that was the wrong folder. Let me correct that. We want to go into the source folder. Now, if we try this, we will create the publisher test package, and here in publisher test package, we want to create a new file, and we're gonna call it publisher test node.py. Don't forget the extension. Let's just wait for it to update. So now when we go to that directory, we can see it down here with init.py. What we need to do now is do this command, so it's actually executable. Now that we've completed that, we also need to do another thing, so don't forget this. You need to go to setup Pi and add this here. So this is just the minimal setup for so you can create a node that it works. There's a lot of more detail and a lot of people going into more detail on how everything works. I'm just showing you the simplest possible way of doing this. And now I'm just gonna put a random code that's gonna publish some stuff, and that's it. So let's take a look at the structure of the code. It's rather simple. We just need to create one publisher, and we're gonna print counter, which is just an int value in a loop. So we need to save that. That's the whole thing. Now we go to here, and we want to build a package. The way you do this is you do colcon build, but that's if you want to build all of the packages that you actually have. But to just save up a bit on time, let's just build our new package. To do that, this will be this, and we just wait for the build to finish. While that is working, let's just add another terminal. Okay, so now it's finished. Now what you need to do is source the setup.bash, and this is something you always need to do after every build. Let's just do this here as well, just in case. And now we are supposed to be able to run our package. So that would be publisher node test. If you press tab, it will autocomplete. So let's run the node, wait for it. And here you can see that this is just the info, so what the node itself is printing out, and we can see it's working. If we go to the other terminal and just list all of the topics, you can see the counter topic. So if we go ROS2 topic echo counter, wait for it to start, we can see that we're getting all of the data like the node is publishing it. Now imagine this going much quicker, doing some sensor data, and that's how actually nodes communicate between each other when you want some higher speed communication. So that's the rather basics of working with ROS2. Now I'm gonna go and show you the simple node I made for controlling the PlatypusBot, so we can actually start working on it into making it a serious robot platform. We're still in Visual Studio Code, but now looking at the PlatypusBot interface node. So this is the current interface with the commands as you've seen in the Arduino IDE. So the whole idea of this node is we have a service, as I've explained in the drawing, and in a service as a command we send a text message, then gets sent to the robot, and then it executes it. So let's take a look what we need in this node. It's rather similar in form like the previous node we've seen, but here the main difference is this line here. So this is how we create a service, and we use something called the string command. That's just how I called it. we defined that in a separate package called new interfaces. You can find all of the directories and codes down below in the Element 14 community if you want to check them out further. But this is how you define a service. So you have what you actually send to the service request. In my case, this is just a command. Then you separate it with 3 dashes, and this is what you get as a response. This usually just like a success bool, so it's a true or false, and a message where you can just say service call handled successfully or not, stuff like that. So anyway, that's the whole node pretty much. It's rather simple. It just takes that message and then sends it over serial. Now if we go here and check this thing here, we can see whether the Arduino is connected or not. This is essentially like a serial monitor, and now if I spin the wheel by hand, you can see what the Arduino is printing on the serial monitor. So what we want to do here is do ROS to run platypus. This will run the node. Oh, but for some reason it can't open, which is strange because it works here. But okay, maybe that's the reason. Let's try that again. Still says it's busy. Let's restart the Arduino real quick. And let's try now. Yeah, I restarted the Arduino, so now it works. And here we can do a service list. And here you can see the PlatypusBot interface v2, and you can see the things that we're actually interested in is the send serial service. So in the testing I'll show you how we actually send service requests, and you'll see the robot move around. But before that, there are a few details I've added to the PlatypusBot that I think you will like to see. And our PlatypusBot stage 2 is complete. You might think it looks completely the same, but if you remember at the beginning of the clip, I said I added some highly requested additions, so let's add them to the robot and you'll see what I mean. This is the first one and this is the second one. Since it's named PlatypusBot and since I actually guessed the color completely by luck, meet Perry the PlatypusBot. So we have the iconic fedora that's just on the LiDAR, and we have the beacon eyes that will get some camera upgrades in the future, let's just say that. So it's time to test it out with ROS and draw it around on the table. Okay, so it's time to test out Perry the PlatypusBot. As you can see on my screen, I have the node running and I've already done some service calls. So I've placed Perry on the 20 centimeter line, which is this line here. And what we want to do is first send him the relative position command to get him 30 centimeters to the front to the 50 centimeter line. To do this, we want to give him this command, which is the C3 command, with 300 millimeters at, let's say, 200 millimeters per second. When we send that command, you can see Perry moving and actually stopping, not bad, a few millimeters before the line. That's because of the accuracy of the controller and of course the wheel slip that we are not compensating in any way at this point. But let's move him now, for example, at 100 millimeters per second back to the exact same line. So we want him to get here. Let's send that command. You can see he's moving slower, but he stops where he's supposed to stop, which is what we wanted to see. Okay, I'm just gonna move him to the center and then we can try out some different commands. So this is just 10 centimeters. Let's now spin him around using the tank turn command. So the tank turn command is C4. We put the angle, so that would be minus 90 degrees, so Perry is facing us, and let's say for speed again 200. Let's give him that command. And here he is. He actually spins rather nicely by 90 degrees. To calculate how many degrees that is, I just measured the distance between the wheels and used the circumference of the wheel of that diameter. So if we give him a command to spin, for example, for 360 degrees at 250, for example, he should do a full turn. Let's see that. And as you can see, he misses a bit by 5 degrees, for example, but it's not too bad at all. Let's go 2 circles at his maximum speed of 300. That's just limited by the battery and everything. Yeah, that's still a bit more, but still not too shabby. So to get him in line again, that would be, let's say, 70 degrees, and let's lower the speed to 150. Yeah, that's a bit too much, but as you can see, the commands are rather easy to grasp like this. These are just some simple commands that are not something that we will use in the next iterations, where we will just send raw bytes essentially at a much higher rate, where we want to do some more complex algorithms. So let's just drive Perry around a bit and you will see how he performs. There is the manual drive of wheels command also, but not something that we should use here because there's no sensors, no safety or anything like that. We also have the constant speed time move, which we can try, but again, he will just run off the table. So let's just stick to the position and tank turn. So let me type this out. Let's say we want to get off completely from this where he is, from the blue mat. That would be 400 millimeters, and let's say at 250. So he should move to the back or to the left of your frame now. Did I send that correctly? I've been sending it with A instead of P. Okay, that was the error. Let's try now. So yeah, we can now go, for example, half a meter or more to the front, and let's see how he goes at full speed. Not the fastest robot in the world, but still rather nice to drive. Let's give him a small spin by 90 degrees. Drive him forward by 60 millimeters at a lower speed. Turn him around again. So essentially he did a U-turn, and drive him 26 centimeters to the front. So our whole system works, our ROS, our Arduino. Now you may be thinking, this doesn't seem like too fancy for robotics, but we're just putting down the cores of the system, and to actually utilize them in pathfinding algorithms and stuff like that, that's something that we're gonna address in one of the future videos. As a send-off, let's just spin him around a bit at his max speed. Thanks so much for watching Perry the PlatypusBot Stage 2. This time we made the essential upgrades like the beak and the Fedora, of course. We've added a Raspberry Pi 4 that's running ROS to Humble, and it communicates with an Arduino Uno, sending commands for precise field movements because we're using the onboard encoders. I'm still thinking of maybe adding even more precise absolute encoders, but we'll see. For the next iteration, I want to utilize sensors like the LiDAR we have underneath the Fedora, adding some cliff sensors, stuff like that, and getting the communication to work much faster. If there's anything particular that you want to see, or if you have any questions or comments, please leave them down below in the comments or on Element 14 community, and see you next time with the version 3 of the Perry the PlatypusBot.